Okay, welcome back, students. Let's cover section 9.4. Okay, so 9.4 is on vector differential equations. Okay, let's look at a theorem. Okay, let A be an n by n matrix of real constants okay. If A has n linearly independent eigenvectors v1, v2, vn with corresponding real eigenvalues lambda 1, lambda 2, lambda n, then the vector functions x1, x2, to x sub n defined by x sub k equals e to the lambda k t vk are linearly independent solutions to x prime equals ax. Okay, so that homogeneous differential equation on any interval and the general solution is x sub t is equal to c1 x1 plus c2 x2 plus plus c n xn. So let's use some eigenvalues and eigenvectors to solve a differential equation. We've got a system here. It says find the solution to x1 prime is equal to x1 plus 2x2, and x2 prime is equal to 2x1 minus 2x2. Okay, so I can rewrite this as x prime equals ax, such that x1 prime, x2 prime is equal to 1 2, this is my coefficient matrix, 2, negative 2 times x1, x2. Okay, so once again, this implies that 1, 2, 2, negative 2 is my coefficient matrix A. Okay, so let's find the eigenvalues of this matrix here. I'm going to go the determinant of 1 minus lambda, 2, 2, and negative 2 minus lambda. That's going to be equal to 1 minus lambda times negative 2 minus lambda minus 2 times 2. Okay. This equals negative 2 minus lambda plus 2 lambda plus lambda squared minus 4. Okay, and this is going to be equal to lambda squared plus lambda minus 6. And I can factor that into lambda plus 3 and lambda minus 2. Okay, so that gives me lambda equals negative 3. Oops. Okay, lambda equals negative 3. Okay, after I set this equal to 0. And lambda is equal to 2. So let's look at what happens when we have our eigenvalue. Okay, but we need our eigenvector. We have eigenvalue lambda equals negative 3, but I need my eigenvector. Okay, so if I plug this into my into the matrix that I got, so, you know, my basically the A minus lambda I matrix, right? Okay, you know, set that equal to 0, 0. Okay, and we want to solve for, okay, the system of equations. Okay, so we're going to say that 1 minus lambda 2, negative 2 minus lambda. Okay, 0, 0. Okay, I can turn this into an augmented matrix. Okay, and plug in my negative 3, I get 4, 2, 2. And then this is negative 2 minus negative 3, which is plus 1, so this is 1. Okay, 0, 0, augmented matrix. Okay, we RREF this one. It's really easy to see that, okay, this is just going to become 1, 1/2, 0, 0, 0, 0. Okay, so I have x. Okay, x1. I'll just call this x and y. Okay, because they don't necessarily refer back to x1 and x2. So I'll just call this x and y. You can come up with some other variable if you want. Maybe I'll call it a and b. Okay, so because I just want to find my eigenvector. So this is going to be a plus 1/2 b is equal to 0. And so I want a to be equal to negative 1/2 b. Okay, or I can multiply both sides by -2, so -2a is equal to b. Okay, so I'll end up with a and -2a. If I factor out the a, or I could have used ab, I could have used r and s as well. It doesn't matter. Okay, factor out the a. This is 1 and -2, and so 1, -2 is my eigenvector. Okay, so v1 is equal to 1, -2, and that corresponds to eigenvalue lambda equals -3. So this tells me from my theorem above that x1 is equal to e to the -3t times my vector 1. Okay, so this is x1 is equal to e to the lambda 1 t times v1, right? So that's going to be e to the -3t times 1, -2, okay, for vector 1. Okay, let's do the same process, but with eigenvalue lambda equals 2. So eigenvalue lambda equals 2. Okay, so we're going to get 1 minus lambda, 2, 2, and -2 minus lambda. Okay, 0, 0. Okay, and so this is going to be -1, 2, and 2, and then this is -4. Okay. Okay, and once again, okay, augmented matrix, and we're going to RREF this, and this becomes 1, -2, 0, 0, 0, 0. Okay, which tells me again that a times 1 minus 2b is equal to 0. So that tells me that a is equal to 2b. Okay, so in this case, it's going to be 2bb. Okay, and so I can factor out the b, and I get 2, 1. Okay, and so my vector 2 is equal to 2, 1. Okay, so what's my x2? That's going to be, well, lambda was equal to 2, right? So x2 is equal to e to the 2t times 2, 1, right? Okay, so now we have a possible x1 and a possible x2. So let me just write x1 here as e to the -3t with 1, -2. and x2 equal to e to the 2t, 2, 1. Okay, which is great, but we need to see if these two functions, okay, are in fact linearly independent. If they're not linearly independent, then they're not solutions. Okay. So let's get the Wronskian of this. Okay, x1, x2. Okay, so the top x1 is going to look like this. It's going to look like okay, e to the negative 3. I'm just going to distribute, okay, these, and that's going to be e to the negative 3t, and then negative 2e to the negative 3t, and then that's going to be e to the 2t, and then e to the, sorry, 2e to the 2t, and then e to the 2t. And that should really be the determinant of that. Okay, which is equal to, okay, e to the negative t. Well, I'll multiply it out in the next line. E to the negative 3t times e to the 2t minus negative 2 e to the negative 3t times 2e to the 2t. Okay, so this becomes e to the negative t minus, or plus, basically, plus 4e to the negative t, which is 5e to the negative t, okay, which in fact, let t not equal 0, then this is equal to 5, which is not equal to 0, therefore they are linearly independent. Thus, linearly independent. Okay, that's great. Okay, that tells me that the general solution should look like x of t equals x1, or sorry, c1 x1 plus c2 x2. Okay, so the general solution should look like, okay, c1 times x1, and what was x1 again? It was e to the negative 3t, e to the negative 3t times 1 and negative 2, okay, plus c2 e to the 2t, right? E to the 2t, and then 2, 1. Okay, okay, so we could write this as a vector. So x of t is equal to, we could multiply this out. So I would get c1 e to the negative 3t, okay, on the top, plus c2 e to the 2t on top, okay, and then on the bottom, okay, I would get c1, or sorry, negative 2c1 e to the negative 3t plus, oh, there's a 2 here, I'm sorry. Okay, that's a 2c2 e to the, oh, okay, plus 1, okay, c2 e to the 2t. Okay, and so this would be considered my solution vector. Okay, because it's just it's a column 2 vector. Okay, so this is my solution vector, okay, in matrix form. Okay, I can take this x of t and say, well, that's x1 of t is equal to c1 e to the negative 3t plus 2 c2 e to the 2t, and x2 of t is equal to negative 2 c1 e to the negative 3t plus 1 c2, which is just c2. Okay, c2, I could probably get rid of the 1 there too. c2 e to the 2t, and those are my two solutions. This is my general solution. Okay, also called the scalar solution, because it doesn't involve any matrices. Scalar general solution. Okay, so that's my general solution. This also up here could have been my general solution as well. Okay, but that has column vectors that that is in that general solution. Okay, so what happens? This is all well and good if I have real eigenvalues. What happens if I have complex eigenvalues? Well, we can use the same process, but it's modified a little bit. We only need one eigenvalue and one eigenvector. Okay, so number 2 here, find the particular solution to the vector differential equation x prime equals ax if a is equal to 2, negative 1, 2, and 4, and x naught is equal to 1, 1, negative 3. Okay, so let's find our eigenvalues. We're going to go 2 minus lambda, okay, negative 1, 2, and then 4 minus lambda. Okay, find that determinant, set it equal to 0. Okay, so we're going to get 2 minus lambda times 4 minus lambda minus 2 times negative 1 equal to 0. Okay, so this is going to be 8 minus 2 lambda minus 4 lambda plus lambda squared plus 2 is equal to 0. This combines to lambda squared minus 6 lambda plus 10 is equal to 0. Okay, so this is not factorable. We have to use quadratic formula on this. So lambda equals negative of negative 6 is 6 plus or minus square root of 6 squared, 36 minus 40. Okay, 4 times a times c all over 2a is 2. This is equal to 3 plus or minus I, because we get a square root of negative 4, which is going to, and that's going to cancel with the 2. Okay, so we have complex eigenvalues. Okay, 3 plus I and 3, we'll call that lambda 1, equals 3 plus I, and lambda 2 equals 3 minus I. But we can use one of these to get our two vectors, okay, our linearly independent vectors. And so let's show how we can do that when we have complex conjugates. Okay, as eigenvalues, complex, I should say conjugate eigenvalues. Okay, complex conjugate eigenvalues. I don't like the way that looks. I'll go like this. There we go. Okay. Okay, so let's look at lambda equals 3 plus I. Okay, let's try to find our eigenvectors now. Okay, so I've got 2 minus lambda, -1, 2, and 4 minus lambda. Okay, and then I'm going to augment that with 0, 0. Okay, so this becomes, okay, 2 minus 3 plus I, 2, 4 minus 3 plus I, -1, 0, 0. Okay. Okay, so now this equals 2 minus 3 is -1 minus I. Okay, this is -1, and this is 2, and this is 1 minus I. 0, 0. Okay, so I'd like to get opposites. Okay. Okay, so in order to get opposites, I would have to what would I have to do? I'd have to multiply by 1 minus I on the top. Okay, because I've got a -1, I could factor this out. And I could see what I would get. So this is -1 times 1 plus I, and then a -1, right? And then I've got a 2 and a 1 minus I, 0, 0. Okay. And so I have, okay, a 1 minus I on the bottom and a 1 plus I on the top. If I multiply by 1 minus I on the top, I could cancel these out, this row out. Okay, so let's see what happens when I do that. So I would get 1 minus I, multiply 1 minus I through on the top. I would get -1 and 1 plus I. Okay, and then I would get -1 minus I, 0, it's fine. And then this row doesn't change. This is 2, and then 1 minus I, okay, and then 0. If I added these two rows together, I would get 1 minus I times 1 plus I times -1 plus 2, and then these two would cancel out. Okay. Plus this would be, I would get a 0 there. Or do I want to do that? Yeah, it doesn't matter. I got the 0 there first. Okay, plus 0. Okay, is equal to 0. And 0, 0. Okay, that's on top. Now this 1 minus I, 1 plus I. Okay, this 1 minus I, 1 plus I, that just becomes 1 plus 1, which is 2. So this really goes to I'm sorry, it's 1 minus, this is 1 minus 1, because this becomes -1 times 1 squared minus I squared plus 2, 0, 2, 1 minus I, 0. Okay, that's good. Okay. And then this becomes 1 minus -1. Okay. So I think that just goes to 0, right? Two, right? I think so. Okay, so this is 1 minus -1. Oh no, that goes, yeah. And then I have a -1 plus 2, 0, 0. And then I have a 2 on 1 minus I, and then a 0. Okay, and this is going to be plus 2. But when I have that -1, that's minus 2 plus 2. And so this whole thing goes to 0. And so I end up with a row of zeros. Okay, I end up with, I could write this as 2, 1 minus I, 0, and then 0, 0, 0. Yeah. Yeah, I like that. Okay. And so what do we get? Well, we get, I'll just use R this time. We get Rness, A and B, whatever you want to use. We'll just use A and B again. So 2A plus 1 minus IB is equal to 0. Okay. And so if I solve, okay, for A, I get, toss that over there, I get 2A equals I minus 1 times B. Okay, all divided by 2. We get A equals I minus 1 over 2 times B. Okay. Okay, so if I write this as I minus 1 over 2 times and B, times B, and then B, and I factor out the B, okay, I can get what? I can get I minus 1 over 2 and then 1 as an eigenvector. I think what I'm going to do, I don't like that fraction. So what I think I'm going to do here is I'm going to let B let B equal to A. Okay, and so then, right? No, 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 no. No. So this is going to be 2a is equal to, let me not divide by 2. I don't like the division by 2 there. Okay. Okay, and so so 2a is equal to, I'll just do -1 plus I times b. Okay, so 2a is equal to that times b. So what do I want? I want this to be 2a is equal to that. So let b, so if a is equal to, let's think about this for a second. Oh, I'm going to use a third variable. That's what I'm going to need to do. Okay, -1 plus I times b over 2. If I let b, let's say b equal to 2c, okay, then a would be equal to -1 plus ic. Yeah, there we go. And b, that's going to end up being -1 plus I and c and 2c. There we go. That makes sense. That works. And so factor that out. So I get c times -1 plus I times 2. Okay, I didn't like having to work with that fraction. Okay, so vector, my eigenvector here, okay, is going to be equal to -1 plus I over 2. Okay. Okay. Okay, so going back to this guy, if lambda I is equal to 3 plus I, or lambda 1, we'll say, call this V1 too if you want. Lambda 1 is equal to 3 plus I, we get, this is our vector. Okay, maybe I'll write it like this. For lambda 1 equals 3 plus I, right? Okay, and we go back to, well, what's x sub I equal to, or x sub 1 in this case? Not x sub 1. Let's call this u sub 1, okay, or u of t. Then this is going to be e to the 3 plus 1 power, or 3 plus I power, times t, times my eigenvector of -1 plus I and 2. Okay, now what we can do with this, okay, that just goes back to our theorem at the very beginning. Let me show you. Okay, we had x of k equals, but it's really not going to be x of k because we're going to actually end up with two vectors here out of this one eigenvalue, and I'll show you. So that's why we call it u instead of x, because it's really not x1 or x2 yet, but I'm going to pull x1 and x2 out of this. Okay, and the way that I do that is using Euler's formula. Okay, so this is, oops, oh, yeah. So this is e to the 3t, okay, times the cosine of t plus I sine of t times -1 plus I over and 2. Okay, so u of t, we're calling u of t, is going to be equal to e to the 3t times, I'm going to multiply this out. Okay, the bottom's a lot easier to multiply out, but we'll get there. Okay, so this is -1 plus I times cosine t plus I sine t. And then this is 2 times cosine t plus I sine t. Using Euler's formula. Okay. So now let's distribute. We get e to the 3t times negative cosine. We're going to distribute the -1 first. Okay. Negative cosine t plus minus I sine t. Okay. And then now this becomes plus I cosine t plus I squared. Okay. Plus I squared sine t. Okay, on the top. And this becomes 2 cosine t plus 2I sine t on the bottom. Okay, well, the I squared is -1. Okay, so I can replace this with a -1 and factor out the negative from the cosine t and the sine, and I would get negative cosine t plus sine t, cosine t plus sine t. Okay, and then this would become plus I times sine t plus cosine t. Okay. And the bottom would become 2 cosine t, and then this would be plus 2I, okay, sine t. Okay, I'm going to rewrite this as I times 2 sine t, okay, and you'll understand in a minute why I did that. Okay, okay, and so this is times e to the 3t. Okay. Okay, so we can use this now. I'm going to break this up into this times this. Okay, or actually, let me not skip a step. Let me go back here. Okay, because the goal is to factor out that I there. Okay, 3t. Okay, and so I'm going to rewrite it like this. E to the 3t times negative, I guess I don't have to factor out the negative, cosine t minus sine t over 2 cosine t, okay, plus I times sine t plus cosine t, and then 2 sine t. Okay, so we got that. And so we can just say that if we take each of these individually, okay, if I were to distribute my e to the 3t, this is e to the 3t times negative cosine t minus sine t over 2 cosine t plus I times e to the 3t times sine t plus cosine t over 2 sine t. Okay. If I take these individually, this is going to be my x1. It's just going to be this guy here. And x2 is this guy here. So this is x1 and this is x2. Okay. The real component is one solution, one part of the solution to the differential equation. And the imaginary component is another solution. Let me move this down here. Okay, so x1 of t is equal to e to the 3t times, okay, negative cosine t minus sine t times 2 cosine t. Okay, and x2 of t is equal to sine t plus cosine t, and then 2 sine t. Okay. And so what's my general solution? Well, my general solution for x of t is equal to c1 times x1 plus c2 times x2. So x of t is equal to c1 times x1, which is e to the 3t times negative cosine t minus sine t times 2 cosine t, okay, plus c2. Oh, there's an e to the 3t that I forgot there. X c2 e to the 3t times sine t plus cosine t over 2 sine t. Okay, and that's my general solution. Okay, so that's the general solution. Okay, but what's the particular solution? Okay, well, they tell me that for x naught, we have 1 and negative 3. Okay, so I'm going to do x1 is equal to, okay, c1 e to the 3t times negative cosine t minus sine t. Oops. Okay, plus c2 e to the 3t times sine t. Oops, I keep putting those brackets. Okay, sine t plus cosine t. Okay, that's c1. Okay, but when we evaluate that at 0, okay, we're going to plug in zeros here. 0, 0, 0, 0, 0, that equals 1. Okay, so x1 of 0. Okay, so that gives me, the signs all go to zeros. Okay, and the e's go to ones. Okay, so that goes away, that goes away. And so I'm just left with negative 1 here. So negative c1 plus c2 is equal to 1. Okay. Negative c1 plus c2 equals 1. Okay, so that's 1 there. Okay, and then what's the next one? Well, the next one would be x2 of 0 is equal to, now we're going to go the bottom route, c1 e to the 3t times 2 cosine t plus 2c2 e to the 3t times sine t. Okay, that is equal to -3. Okay, well, again, we're going to plug in our 0, so that goes away. That goes away. This goes to 0, which wipes out that entire one. Okay, and so I'm left with 2c2 or 2c1, okay, equals -3. Equals -3. Okay, so divide by 2, and c1 is equal to -3/2. Okay, so that tells me that c2, because of this guy up here, that equals 1/2. Right? Is that right? No, that is equal to 2. Sorry. C2, C1 is negative. Oh, yeah, it should be -1/2, right? Yeah. Because I would plug that in, and they have to add up to 1. Yes. Okay, so now my particular solution, okay, is x of t is equal to, okay, -3/2 e to the 3t, okay, times, let me go back up here, times negative cosine t minus sine t, and then we had 2 cosine t. Okay. Plus, okay, -1/2 or -1/2. Okay, and then this was sine t plus cosine t. And then 2 sine t. Oh, and there's, sorry, e to the 3t is there. Okay, and then again, I could leave this in this form, or I could write out my particular solution in scalar form. So this is vector form. Okay, this is my solution vector. Okay, and so x1 of t is equal to -3/2 e to the 3t times, I'm gonna times negative cosine t minus sine t. Okay, -1/2 e to the 3t times sine t plus cosine t. Okay, I should be able to simplify this. Okay, so this is equal to, factor out the e to the 3t, and distribute this and distribute this. I should end up with 3/2 cosine t plus 3/2 sine t okay, minus 1/2 cosine t minus 1/2 sine t. The other way around. 1/2 sine t minus 1/2 cosine t. Okay, which is just going to give me a cosine, 1 cosine and 1 sine. So x1 is equal to e to the 3t times cosine t plus sine t. Okay, that's cool. what's x2? Okay, x2 of t is going to be equal to, okay, this is going to be e to the 3t, negative 3 halves e to 3t times 2 cosine t, okay, minus 1/2 e to the 3t times 2 sine t. Okay, so this just becomes, factor out the e to the 3t, that's e to the 3t times negative 3 cosine t, okay, and then this is minus 1 sine t, okay, and that's x2. So my particular solution, okay, is x1 equals e to the 3t times cosine t plus sine t, and x2 of t, I should probably put up t here because it's my final answer. Come on. X1 of t equals, and then x2 of t is equal to e to the 3t times negative 3 cosine t minus sine t. And there you go. There's my particular solution. Okay. Okay. So that is 9.4, chapter 9. And I'll see you in the next chapter. Okay.